sklearnmetrics, pairwise, kernel metrics. Description. The kernel metrics function in scikit-learn provides a convenient way to compute pairwise kernel values between samples. It's particularly useful in machine learning algorithms that rely on kernel functions for similarity calculations, such as support vector machines (SVMs) or kernel-based clustering. Inputs. X. The input data, typically a 2D array where each row represents a sample. Y. An optional second input data array. If not provided, it defaults to X, allowing calculation of pairwise kernels within the same dataset. Metric. The kernel function to use. This can be a string representing a built-in kernel, e.g., linear, RBF, poly, or a callable function that implements the kernel. Outputs. Kernel values. A 2D array representing the pairwise kernel values between samples. The shape of this array is n samples x, n samples y. Steps. 1. The function first determines the type of kernel function to use based on the provided metric argument. 2. It then iterates through all pairs of samples from x and y, calculating the kernel value for each pair using the specified kernel function. Metrics. Kernel type. The kernel function determines how the similarity between samples is calculated. Common kernel types include: linear calculates the dot product between samples. RBF radial basis function measures similarity based on the distance between samples, using a Gaussian-like function. Polynomial calculates a polynomial function of the dot product between samples. Visualization plots. Kernel heat map. A heat map can be generated to visually represent the pairwise kernel values. This can help in understanding the relationships between samples based on the chosen kernel. Fine-tune parameters. Kernel parameters. Many kernel functions have parameters that can be adjusted to influence their behavior. For example, the RBF kernel has a gamma parameter that controls the width of the Gaussian function. Metric argument. You can customize the kernel by specifying a custom callable function as the metric argument. Uncertainty methods. Kernel regularization techniques like adding a small amount of noise to the kernel values can help reduce overfitting and improve model robustness. Challenges and fixes. Challenge 1. Computational complexity. Calculating pairwise kernels can be computationally expensive for large datasets, especially when using more complex kernels. Sample use case training. A SVM with a large dataset and an RBF kernel. Fixes. Subset sampling. Randomly select a subset of samples for kernel computation, especially during model training. Approximate kernels. Use approximate kernel methods that trade off accuracy for speed. Challenge 2. Choosing the right kernel. Selecting the appropriate kernel for a given problem can be crucial for model performance. Sample use case. Using a linear kernel for data that is highly nonlinear. Fixes. Cross-validation. Use techniques like cross-validation to evaluate different kernels and their parameters. Domain knowledge. Utilize domain knowledge to guide kernel selection. Challenge 3. Kernel parameters. Tuning. Optimizing kernel parameters can be time-consuming. Sample use case. Finding the optimal gamma parameter for an RBF kernel. Fixes. Grid search. Explore a range of parameter values using grid search techniques. Random search. Randomly sample parameter values for efficient exploration.